Now that we know what block ciphers are and we know how to construct them, let's see how to use them for secure encryption. But before that, I want to briefly remind you of an important abstraction called a pseudo-random function and a pseudo-random permutation. So as we said in the last module, block ciphers map n bits of inputs to n bits of outputs, and we saw two examples of block ciphers, triple DES and AES. Now, an important abstraction of the concept of a block cipher is captured by this idea of a PRP and a PRF. And remember that a pseudo-random function, a PRF, basically is a function that takes two inputs. It takes a key and an element in some set X, and it outputs an element in some set Y. And for now, the only requirement is that there's an efficient algorithm to evaluate this function. We're going to talk about security for PRFs in just a minute. And then similarly, there's a related concept called a pseudo-random permutation, which is similar to a PRF. In fact, there's also an efficient algorithm to evaluate the pseudo-random permutation. However, there's an additional requirement that there's also an algorithm D that will invert this function E. So a PRP is basically a PRF, but where the function is required to be one-to-one for all keys, and there's an efficient inversion algorithm. So now let's talk about how to define secure PRFs. So we already said that essentially the goal of a PRF is to look like a random function from the set X to Y. So to capture that more precisely, we defined this notation funds xy to be the set of all functions from the set X to the set Y. Similarly, we defined the set S sub f to be the set of all functions from the set X to Y that are defined by the PRF. In other words, once you fix the key k, you obtain a function from the set X to the set Y, and the set of all such functions given a particular PRF would be the set S sub f. So as we said last time, funds xy is generally a gigantic set of all functions from X to Y. I think I mentioned that, in fact, for AES, where X and Y are 2 to the 128, the size of this set is 2 to the 128 times 2 to the 128. It's a double exponential, which is an absolutely enormous number. On the other hand, the number of functions defined by the AES block cipher is just 2 to the 128, namely one function from each key. And what we'd like to say is that a random choice from this huge set is indistinguishable from a random choice from this small set. And what do we mean by indistinguishable? We mean that an adversary who can interact with a random function in here can't distinguish that interaction from an interaction with a random function in here. Now let's define that more precisely. So we're going to, as usual, define two experiments, experiment 0 and experiment 1, and our goal is to say that the adversary can't distinguish these two experiments. So in experiment 0, the challenger basically is going to choose a random pseudo-random function. Okay, so he's going to fix the key k at random, and that's going to define this function little f over here to be one of the functions implemented by the PRF. In experiment 1, on the other hand, the challenger is going to choose a truly random function from the set X to the set Y, and again we're going to call this truly random function little f. Either way, in either experiment 0 or experiment 1, the challenger ends up with this little function f that's either chosen from the PRF or chosen as a truly random function from X to Y. Now the adversary basically gets to query this function little f. So he gets to submit a query x1, and he obtains the value of f at the point x1. Then he gets to submit an x2, and he obtains the value of f at the point x2. And so on and so forth. He makes q queries, and so he learns the value of the function little f at those q points. And now his goal is to say whether the function little f is chosen truly at random from funds xy, or chosen just from the set of functions implemented by the PRF. So he outputs a certain bit b prime, and we'll refer to that output as the output of experiment, either experiment 0 or experiment 1. And as usual, we say that the PRF is secure if, in fact, the adversary can't distinguish these two experiments. In other words, the probability that he outputs 1 in experiment 0 is the same, pretty much the same, as the probability that he outputs 1 in experiment 1. In other words, the difference of these two probabilities is negligible. So this captures nicely the fact that the adversary couldn't distinguish a pseudo-random function from a truly random function from the set X to Y. Now the definition for a secure pseudo-random permutation, a secure PRP, which is basically a secure block cipher, is pretty much the same. In experiment 0, the adversary is going to choose a random instance of the PRP, so he's going to choose a random k and define little f to be the function that corresponds to little k within the pseudo-random permutation. In experiment 1, the adversary is going to choose not a truly random function from X to Y, but a truly random one-to-one function from x to x. Okay, so the goal of our PRP is to look like a random permutation from x to x, namely a random one-to-one function from the set x to itself. So the little function, little f here, is again going to be a random function from the set x to itself. And again, the challenger ends up with this function, little f. As before, the adversary gets to submit queries, and he gets to see the results of those queries, and then he shouldn't be able to distinguish, again, experiment 0 from experiment 1. So again, given the value of the function f at q points chosen by the adversary, he can't tell whether the function f came from a PRP or whether it's a truly random permutation from x to x. So let's look at a simple example. Suppose the set x contains only 2 points, 0 and 1. In this case, perms x is really easy to define. Essentially, there are 2 points, and we're looking at 0, 1, and we're asking what is the set of all invertible functions on the set 0, 1? Well, there are only 2 such functions. One function is the identity function, and the other function is basically the function that does crossovers, namely this function here. These are the only 2 invertible functions in the set 0, 1. So really, perms x only contains 2 functions in this case. Now let's look at the following PRP. The key space is going to be 0, 1, and of course x is going to be 0, 1. And let's define the PRP as basically x XOR k. Okay, so that's our PRP. And my question to you is this a secure PRP? In other words, is this PRP indistinguishable from a random function on perms x? I hope everybody said yes, because essentially the set of functions implemented in this PRP is identical to the set of functions in perms x. So a random choice of key here is identical to a random choice of function over here, and as a result, the 2 distributions, either pseudo-random or random, are identical. So clearly an adversary can't distinguish the 2 distributions. Now, we already said that we have a couple of examples of secure PRPs, triple DES and AES, and I just wanted to mention that if you want to make things very concrete, here's a concrete security assumptions about AES. Just to give an example, say that all algorithms that run in time 2 to the 80 have advantage against AES of at most 2 to the minus 40. This is a reasonable assumption about AES, and I just wanted to state it for concreteness. So let's look at another example. Consider again the PRP from the previous question, namely x XOR k. Remember the set x was just 1 bit, namely the values 0 and 1. And this time we're asking, is this PRP a secure PRF? In other words, is this PRP indistinguishable from a random function from x to x? Now the set of random functions from x to x, funds xx, in this case contains only 4 elements. There are the 2 invertible functions, which we already saw, namely the identity function and the negation function, the function that sends 0 to 1 and 1 to 0. But there are 2 other functions, namely the function that sends everything to 0 and the function that sends everything to 1. Okay? These are 4 functions inside funds of xx. And the question is this PRP that we just looked at, is it also indistinguishable from a random choice from funds xx? So I hope everybody said no, and the reason it's not a secure PRF is because there's a simple attack. Namely, the attacker is supposed to distinguish whether he's interacting with this PRP or is he interacting with a random function from funds xx. And the distinguisher is very simple. Basically, we're going to query the function at both x equals 0 and x equals 1. And then if we get a collision, in other words, if f of 0 is equal to f of 1, then for sure we're not interacting with a PRP, in which case we can just output 1. In other words, we're interacting with a random function. In other words, we say 0. So let's look at the advantage of this distinguisher. Well, when it's interacting with a PRP, we'll never output a 1 because f of 0 can never be equal to f of 1. In other words, the probability of outputting 1 is 0. However, when we interact with a truly random function in funds xx, the probability that f of 0 is equal to f of 1 is exactly 1/2, because half the functions satisfy f of 0 is equal to f of 1 and half the functions don't. So then we'll output 1 with probability 1/2. So the advantage of this distinguisher is 1/2, which is non-negligible, and as a result, this PRP here is not a secure PRF. Now it turns out this is only true because the set X is very small, and in fact there's an important lemma called the PRF switching lemma that says that a secure PRP is in fact a secure PRF whenever the set X is sufficiently large. And by sufficiently large, I mean, say, the output space of AES, which is 2 to the 128. So by this lemma, which we'll state more precisely in a second, AES, if it's a secure PRP, it is also a secure PRF. So the lemma basically says the following: if you give me a PRP over the set X, then for any adversary that queries the PRP at most Q points, so it makes at most Q queries into the challenge function, then the difference between its advantage in attacking the PRP when compared to a random function is very close to its advantage in distinguishing the PRP from a random permutation. In fact, the difference is bounded